Picture this. A highly respected scientist has just finished delivering this sweeping public lecture on astronomy.
Oh, I know this one. It's a classic.
Right, so he spent the last hour explaining how the Earth orbits the sun and how the sun orbits the center of our vast galaxy.
Standard stuff, yeah.
Exactly. So right as he wraps up and takes questions, a little old lady at the back of the room stands up and declares, "What you have told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise."
Wow. Bold claim.
Yeah, and the scientist, he gives this incredibly condescending little smile and asks, "Well, what is the tortoise standing on?"
Thinking he's won the argument.
Exactly.
Yeah.
But the old lady doesn't miss a beat. She fires right back, "You're very clever, young man, very clever. But it's turtles all the way down."
That is just, it's such a brilliant, funny way to illustrate the fundamental problem of human cosmology, you know?
It really is.
Because throughout history, we constantly convince ourselves that we finally have the ultimate absolute picture of reality.
Right, like we've solved it.
Exactly. Only to discover that our entire foundational understanding is resting on something completely unexpected and honestly really bizarre.
And that is our mission for you today. We are doing a deep dive into the source material of a true modern classic, which is Stephen Hawking's A Brief History of Time.
An absolute masterpiece.
It really is. We want to take you on a journey out of that ancient, rigid view of a tortoise-supported cosmos, drag you through the absolute mind-bending realities of relativity and quantum mechanics,
Just quite a trip.
and drop you off at the ultimate cosmic mystery, which is black holes.
It requires a massive shift in how you view your own existence, honestly.
Oh, totally.
Because the texts we're looking at, they chart a course from a universe that humanity desperately wanted to believe was this comfortable, unchanging stage into a dynamic, explosive, and highly unpredictable reality where time itself is flexible.
Okay, let's unpack this.
Okay.
Because to truly appreciate how utterly bizarre black holes are, we first have to understand the arena they exist in.
Right, the stage itself.
Exactly.
Yeah.
Because for a long time, humanity just operated under the assumption that the sky was this, static dome of stars just twinkling above our heads.
Well, the desire for a permanent, unchanging universe is deeply baked into human psychology. I mean, if we go all the way back to 340 BC, Aristotle had actually deduced that the Earth was a round sphere, not a flat plate.
Wait, really? That early?
Yeah. He figured this out by observing lunar eclipses, noting that the Earth's shadow cast on the moon was always curved.
Okay, that makes sense.
And travelers also reported that the North Star appeared lower in the sky the further south they went, which, only makes sense on a spherical surface.
But the catch is, Aristotle still placed this round Earth completely stationary at the center of everything.
Right, the center of the universe.
Yeah, and then Ptolemy came along and built a highly complex mathematical model around that idea. He visualized the Earth, surrounded by these 8 rotating crystal spheres that carry the sun, the moon, and the stars.
Which sounds beautiful, honestly.
It does. And it was the unquestioned model for over a millennium.
Because it validated our human-centric intuition, But cracks started to form. Like in 1514, Copernicus secretly circulated his idea that the sun was actually stationary at the center.
Secretly, because of the church, right?
Exactly. Then a century later, Kepler realized the planets didn't move in perfect divine circles, but in ellipses.
Oh, right.
And suddenly, the mathematical predictions actually matched the messy observations in the sky. The Earth was just another rock in motion.
Which brings Isaac Newton onto the field in 1687. He drops his law of universal gravitation, basically declaring that every single body in the universe attracts every other body.
The heavier it is, the stronger the pull.
Right. Now, the source text points out a massive logical puzzle this created for Newton.
Oh, the collapse problem.
Yes. If gravity is always pulling things together, and the universe is just a finite cluster of stars, shouldn't they all just violently attract each other and eventually collapse into one massive pile?
That was the glaring flaw in his whole system. So, to avoid the terrifying concept of a collapsing universe, Newton argued that the universe must be completely infinite.
Endless stars.
Endless, filled with an infinite number of stars distributed evenly. Because if it's infinite, there is no quote-unquote center for everything to collapse into.
That feels like a bit of a mathematical cheat code.
Oh, it totally was.
Yeah.
He thought the gravitational poles would cancel each other out, keeping the universe perfectly static. Even Einstein, much later, altered his own equations with a cosmological constant just to maintain this comforting illusion of a static universe.
But then in 1929, Edwin Hubble completely shatters that illusion.
Yes, the Doppler effect.
Yeah, using the
Yeah.
Doppler effect. Now, for you listening, normally you experience the Doppler effect with sound. Think about standing on a sidewalk when an ambulance speeds past you.
Right, the siren changes pitch.
Exactly. The siren is really high-pitched as it compresses the sound waves coming towards you, and then the pitch suddenly drops lower as it speeds away, stretching those waves out. Well, Hubble realized you can do this exact same thing with light.
Because light travels in waves too. And instead of pitch, our eyes perceive the frequency of those light waves as color.
Okay.
So Hubble started analyzing the light arriving from distant galaxies. If a galaxy was moving toward us, the light waves would compress, shifting toward the blue end of the spectrum.
But he didn't see blue, did he?
No,
Yeah.
he saw almost the exact opposite. The light from nearly all distant galaxies was stretched out, shifted toward the red end of the spectrum.
Meaning they're all moving away from us.
Yes.
And the kicker is, the farther away a galaxy was, the faster it was moving away. Like the universe wasn't just sitting there. It was actively expanding in every direction, inflating like a balloon.
And the definitive proof of this dynamic universe arrived in 1965, incredibly by pure accident.
This is my favorite story in the whole book.
So good. Arno Penzias and Robert Wilson were testing this highly sensitive microwave detector for satellite communication, but they kept picking up this persistent, frustrating background noise.
Like a hiss or static.
Exactly. And it didn't matter which direction they pointed the antenna. The static was always there.
I have to highlight the funniest detail from the text here.
Yeah.
They were so baffled by this static that they actually assumed a flock of pigeons roosting in the antenna was to blame.
Yep. They thought it was the birds.
They literally climbed in there and scraped out a mountain of pigeon droppings, thinking the heat from the poop was causing the interference.
Two brilliant physicists doing literal dirty work.
Just scrubbing out the antenna.
But it turned out the static wasn't bird droppings. They had inadvertently detected the cosmic microwave background radiation.
Wow.
Because when you look out into deep space, you are essentially looking back in time, since light takes time to reach us.
Right.
So Penzias and Wilson were literally hearing the cooled down, stretched out, leftover echo of the incredibly hot, dense early universe.
Which conclusively proves the universe hasn't always been the way it is now. It evolved.
Yeah.
But let me push back on something from earlier, actually.
Sure.
The text mentions Newton's realization that there is no absolute rest in the universe.
Yeah.
Like, if you are playing ping pong on a moving train, the ball obeys the exact same laws of physics, whether the train is traveling at a smooth 90 miles an hour or if it's parked at the station. You cannot feel the speed.
Correct.
So, if everything is moving relative to everything else, and gravity is this relentless force constantly trying to pull all matter together, why didn't the universe just collapse before it could even get the chance to expand?
What's fascinating here is that the universe is expanding at a highly specific, critical rate. It is this incredibly delicate cosmic balancing act.
Okay, how so?
Think of a rocket launching from a launch pad. If the rocket is moving too slowly, Earth's gravity wins and it crashes back down.
Right.
But if it hits escape velocity, which is about 7 miles per second, the rocket's outward momentum is just enough to overcome gravity and it escapes into space.
Oh, I see.
The universe's initial expansion was perfectly balanced against the inward crush of its own gravity. And logically, if the universe is expanding outward today, running the clock backward means at some point in the past, all the matter and energy in the universe was crammed into the exact same microscopic space.
The Big Bang. A single point of infinite density.
Exactly, a singularity. Stephen Hawking and Roger Penrose use mathematical proofs to show that if our understanding of gravity is correct, the universe absolutely had to begin from a singularity.
But this brings up a massive problem. We only discovered all this expansion by analyzing light from distant galaxies. Light is the messenger, basically.
Yes, the ultimate messenger.
But when scientists actually scrutinized how that messenger travels, the entire fabric of reality unraveled.
It really did. At the end of the 19th century, physicists were convinced that light waves needed a visible medium to travel through, much like sound needs air or ripples need water.
Because waves have to wave through something.
Right. So they called this invisible, universe-spanning substance the ether. The assumption was that, since the Earth is hurtling through space, we are basically swimming through this ether.
Okay.
Therefore, a beam of light fired in the direction the Earth is moving should measure faster than a beam fired in the opposite direction.
Like swimming with the current versus against it.
Exactly.
But in 1887, the Michelson-Morley experiment shattered that assumption. They built this incredibly precise device to measure light beams traveling at right angles to each other.
A really ingenious setup.
Yeah, and no matter what time of year they measured it or what direction the Earth was moving, the speed of light was exactly the same. The ether just didn't exist.
Which was baffling at the time. But this paved the way for young Albert Einstein to step in with his theory of special relativity in 1905.
Here we go.
Einstein argued that the laws of science should be exactly the same for all freely moving observers, and critically, the speed of light is a constant for everyone no matter how fast they are moving.
But if the speed of light is completely rigid and speed is simply distance divided by time, a mathematical paradox emerges, right?
Something has to give.
If the speed can't change, then the distance and the time have to be the things that change. Space and time must stretch and compress. There is no master clock ticking away in the background of the universe.
It's completely relative to the observer, and a decade later, Einstein expanded this into general relativity, which totally overthrew Newton's model of gravity.
Because Newton thought gravity was this invisible tether pulling objects together across empty space.
Exactly. But Einstein realized that space and time are actually woven together into a four-dimensional fabric, and massive objects don't just sit on this fabric, they warp it.
The source text has this fantastic visual analogy for this. Think of an airplane flying over heavily rolling, hilly ground.
I love this analogy.
Yeah, so in three-dimensional airspace, the plane is flying in a perfectly straight, unbending line. But if you watch the plane's shadow moving across the 2D hilly ground below, that shadow follows a curved, bending path over the contours of the hills.
Right.
That is what planets are doing. They are moving in completely straight lines through four-dimensional space-time, but because a massive object like the sun bends that space-time into a deep bowl, it looks to us like the planets are moving in circular orbits.
So space and time are no longer just an empty, passive theater where events take place. They are dynamic, flexible participants affected by everything in the universe.
But hold on, I want to clarify what this actually means for the human body.
Okay, sure.
If time is relative, and time bends in the presence of heavy gravity, does that literally mean my feet are aging at a different rate than my head, simply because my feet are closer to the gravitational pull of the Earth?
It literally does.
That is wild.
I know. Now, the gravitational difference between your head and your feet is so incredibly small that the time dilation is imperceptible to a human. But it is entirely real. In fact, in 1962, physicists tested this by placing two incredibly accurate atomic clocks on a water tower.
One at the top, one at the bottom.
Yes. One at the very top, one at the very bottom. And the clock at the bottom, which was sitting deeper in the Earth's gravitational well, actually ticked slower than the one at the top.
That is just mind-blowing.
And it isn't just theory either. It directly impacts your daily life. Consider the GPS satellites orbiting the Earth that power the navigation app on your phone.
Okay.
Those satellites are much further away from the Earth's center of gravity than you are, so their onboard clocks actually run slightly faster than the clocks on your phone.
Wait, really?
Yes. If engineers didn't program those satellites to mathematically account for general relativity, your navigation app would start failing within hours, drifting off by miles every single day.
Wow. Okay, so general relativity perfectly handles the macro universe. Planets, stars, heavy gravity.
The big stuff.
Yeah, the big stuff. But if we want to figure out how the universe began at the Big Bang singularity, we have to deal with the unimaginably small. And when we zoom into the microscopic realm, gravity takes a backseat and the rules change entirely.
We enter the world of quantum mechanics. And to understand why this was so shocking to physicists, you have to realize that since the 19th century, scientists believed in Laplace's dream of scientific determinism.
Oh, right, the clockwork universe.
Exactly. The idea was simple. The universe is a giant, predictable machine. If we knew the exact position and speed of every particle in the universe right now, we could use the laws of physics to predict the entire future with absolute certainty.
But in 1926, Werner Heisenberg steps up and completely ruins the clockwork with his uncertainty principle.
He really threw a wrench in it.
He proved that it is physically impossible to measure both the exact position and the exact velocity of a particle at the same time. Like, the more accurately you try to pin down where a particle is, the less you can possibly know about how fast it's moving, and vice versa.
And the mechanism behind this is entirely logical when you actually think about observation.
How so?
Well, to see an electron, you have to bounce something off of it, like a tiny packet of light called a photon. But an electron is so small that the very act of a photon hitting it transfers energy to it, knocking the electron onto a completely new trajectory. You cannot observe the quantum world without altering it.
So what does this all mean? Let's say you're in a pitch-black room trying to figure out the exact position of a rolling billiard ball.
Okay, good analogy.
The only tool you have to find it is to blindly throw other billiard balls into the dark. By the time you hear the click and figure out where the target ball was, your thrown ball has violently smashed into it, sending it spinning away at a new, unknown speed. You destroyed the determinism you were trying to measure.
That is exactly how it works. And because we can never know the exact present state of the universe, we can never perfectly predict the future. Quantum mechanics forces us to accept a universe governed by probabilities.
Just chances and statistics.
Right. It also forced physicists to accept wave-particle duality, which states that particles don't just act like solid little spheres, they also behave like sprawling waves.
This is best shown by the famous two-slit experiment, right?
Yes.
If you fire a beam of solid objects, like bullets, at a wall with two tiny slits, you get two distinct clusters of bullet holes on the wall behind it.
Right, because they go through one slit or the other.
But if you fire electrons through those two slits, you don't get two clusters. You get an interference pattern, a series of bands spreading out across the back wall, exactly like ripples of water colliding and overlapping.
And the truly baffling part is that even if you slow the gun down and fire just one single electron at a time, so there are no other electrons to bounce off of, the interference pattern still slowly builds up on the back wall.
That's the part that hurts my brain.
I know. That means a single electron is traveling as a wave, passing through both slits simultaneously and interfering with itself before hitting the back wall.
A particle being in multiple places at once. It defies all common sense. And when physicists dug even deeper into these particles, they found that protons and neutrons aren't even the fundamental building blocks of matter. They are made of even smaller entities called quarks.
Right. Quarks come in different flavors, which physicists named up, down, strange, charmed, bottom, and top.
Very creative naming there.
And as an amusing side note, the name quark was actually lifted from a highly obscure line in a James Joyce novel. 3 quarks for muster mark.
Which proves theoretical physicists still appreciate good literature.
Apparently so.
But practically, how do all these quarks actually interact to build the universe we see?
They are governed by 4 fundamental forces, which we briefly need to outline. First, gravity, which is actually the weakest force, but it operates over vast cosmic distances.
Right.
Second, the electromagnetic force, which governs how electrons interact with nuclei, creating chemistry and light. Third, the weak nuclear force, which operates only at the microscopic level and is responsible for things like radioactive decay.
Okay, and the fourth?
The strong nuclear force. This one is carried by particles appropriately named gluons, which act like the superglue holding the quarks together inside protons and neutrons.
Which perfectly brings us to a wildly dangerous aspect of the quantum world, antimatter.
Oh, yes. In 1928, physicist Paul Dirac developed equations that successfully married quantum mechanics with special relativity. But his math had a very surprising byproduct. It predicted that for every particle of matter, there must be a corresponding antiparticle.
Like an evil twin.
Basically,
Yeah.
an anti-electron, an antiquark. These antiparticles have the exact same mass but opposite electrical charges. If a particle of matter ever touches its antimatter twin, they instantly annihilate each other in a massive burst of pure radiation.
This raises an important question.
Yeah.
If the Big Bang created a universe packed with equal amounts of matter and antimatter, why didn't everything just instantly annihilate?
Right.
The universe should just be a glowing soup of radiation. Why is there any solid matter left over to create galaxies, our planet, and us? We literally shouldn't exist.
It is the ultimate existential question. And the answer lies in a tiny imperfection in the laws of physics. The weak nuclear force doesn't behave perfectly symmetrically.
What do you mean?
If you were to swap all particles for antiparticles and run time backward, the weak force actually operates just a tiny bit differently. Because of the slight imbalance during the unimaginably extreme heat of the early universe, the matter and antimatter didn't cancel each other out perfectly.
Oh, wow.
Yeah, for every billion pairs that annihilated each other, 1 extra particle of matter survived.
We are the universe's leftovers.
Pretty much.
The tiny fraction of a percent of matter that survived the initial cosmic battle, that is unbelievably humbling. Okay, so we have general relativity governing the massive and quantum mechanics governing the tiny. But what happens when you take a massively heavy object and crush it down until it becomes extraordinarily tiny?
You get the ultimate cosmic collision of these two theories, a place where our physics literally breaks down, a black hole.
Walk us through how a black hole actually forms. What is the mechanism?
It begins with the life cycle of a massive star. For millions of years, a star is locked in a fierce balancing act. You have the immense, relentless inward crush of the star's own gravity trying to collapse it.
Right.
Pushing back against that is the outward thermal pressure created by nuclear fusion. The star is essentially a continuous hydrogen bomb exploding in its core. But eventually, the star burns through all its nuclear fuel. The explosions stop.
And gravity takes over.
Exactly. Now, for smaller stars, there is a backup defense mechanism. Physicist Subramanian Chandrasekhar calculated what happens as the star shrinks. Remember the Pauli exclusion principle from quantum mechanics?
Yeah, that's the one that states particles cannot occupy the exact same quantum state, right?
Right. Think of electrons like incredibly stubborn passengers on a crowded subway car. They absolutely refuse to share the same seat.
Okay, I like that.
So as gravity crushes the star inward, these particles push back violently against each other to maintain their personal space, creating a new outward pressure that stabilizes the star.
But Chandrasekhar found a limit to this, didn't he?
He did. The Chandrasekhar limit. He proved that if a cold, dying star is more than 1.5 times the mass of our sun, the sheer crushing weight of gravity becomes too strong.
The gravity just overpowers them.
Yeah, the stubborn electrons are overwhelmed. The Pauli exclusion principle cannot stop the collapse.
And the star just caves in on itself entirely. And Robert Oppenheimer realized the terrifying consequence of this. As the star shrinks down, its gravitational pull becomes intensely concentrated. Eventually, the gravity becomes so fierce that the escape velocity, basically the speed required to break free from its pull, surpasses the speed of light.
And since relativity tells us nothing can travel faster than light.
Nothing can escape, not even light itself. It creates a dark spherical boundary in space known as the event horizon.
And when a star crosses that point, it undergoes a bizarre transformation regarding information. All the complex details about that star, whether it was made of matter or antimatter, its chemical composition, its complex shape, all of it is completely erased from the view of the outside universe.
It's just gone.
Physicists mathematically prove this concept, which goes by the rather funny name. A black hole has no hair. Once a black hole forms, it retains only two measurable properties: its mass and its rotation. Every other piece of defining information is lost forever behind the event horizon.
But because no light escapes, we can't see them directly. We have to look for the havoc they cause, right? Like the famous case of Cygnus X1.
Precisely. In the Cygnus constellation, astronomers observed a massive visible star rapidly whipping around an unseen companion. The invisible object's gravity was so intense it was actually tearing gas off the visible star.
Like siphoning it away.
Exactly. As this gas spiraled down into the unseen partner, it heated up to millions of degrees, blasting out powerful X-rays. When they ran the calculations, the invisible object was simply way too massive to be anything other than a black hole.
Here's where it gets really interesting. I want to put the listener right in the middle of this. If I am parked safely in a spaceship a few million miles away, and I watch a brave astronaut fly their pod down and fall into that black hole, what do I actually see happen to them?
You experience a profound optical illusion created by the warping of time.
Okay.
From your safe vantage point in the spaceship, as the astronaut approaches the event horizon, their time appears to slow down dramatically relative to yours. If they are sending you a radio signal every second, those signals start taking longer and longer to reach you.
Because the space-time is stretching.
Right. And the light bouncing off their ship gets stretched by the intense gravity, shifting heavily toward the red end of the spectrum and growing dimmer. To your eyes, it looks like the astronaut gradually slows to a halt, freezing perfectly still right at the boundary of the event horizon, slowly fading into blackness. You never actually see them cross the threshold.
But what is the experience for the astronaut who is actually falling?
For the astronaut, their own time feels completely normal. They would cross the event horizon without feeling a bump or hitting a physical wall. But very quickly, the deadly reality of that extreme gravity gradient would take hold. The gravitational pull on their feet, which are closer to the center of the black hole, would be exponentially stronger than the pull on their head.
Oh, no.
Yeah. The difference in force would stretch their body out vertically while simultaneously crushing them inward horizontally. Astrophysicists have a highly technical term for this exact process:
Which is
spaghettification.
spaghettification. It sounds like a bad cartoon, but it's genuinely terrifying. They're just stretched into a single stream of atoms.
It is a violent end. But the observational evidence for these cosmic monsters became so undeniable that Stephen Hawking famously conceded a long-standing bet he had with fellow physicist Kip Thorne.
Oh, I read about this bet.
Yeah, they had bet on whether Cygnus X1 was actually a black hole. When the data proved it was, Hawking teed up. And per the humorous terms of their wager, he had to buy Thorne a one-year subscription to Penthouse magazine, much to the outrage of Thorne's wife.
I love that humanity's deepest, most profound cosmic mysteries are settled with magazine subscriptions. But as we wrap up, I want to bring all this sprawling science back down to earth for you listening right now.
It's important to ground it.
Right, because why should you care about quarks, wave-particle duality, and warped space-time? Because these aren't just abstract equations sitting on a university chalkboard. These are the invisible, immediate rules dictating your reality.
Absolutely.
That Pauli exclusion principle. That is the specific mechanism keeping the atoms in your body from collapsing into a dense microscopic soup right now, allowing you to actually sit in your chair.
Like holding you together.
General relativity is the active warp in space-time that keeps our planet safely orbiting a yellow star, instead of just hurtling off into the frozen void.
Yeah.
You are a walking, breathing manifestation of quantum mechanics and relativity interacting perfectly.
And yet, despite all this knowledge, the grand puzzle remains incomplete.
Right. The singularity.
Exactly. We know that classical general relativity breaks down completely at the singularity inside a black hole, which is a microscopic point of infinite density where the rules of space and time simply cease to exist.
Okay.
But if you remember, we established earlier that our universe began from a microscopic point of infinite density at the Big Bang. This leaves us with a truly profound speculation to consider.
I love where this is going.
If time essentially ends inside the singularity of a black hole, and time began from the singularity of our Big Bang, could the fiery birth of our universe simply be what happens on the other side of a cosmic event horizon?
Something to seriously ponder the next time you look up at the night sky. The universe might just be black holes giving birth to other universes. Turtles all the way down. Thanks for joining us on this deep dive, and we'll catch you next time.